Greetings, class. Today we're going to start chapter 26, which is on the topic of AC electricity. AC stands for alternating current, and what we're going to see here is examples where the power supply puts out a variable voltage. So far we've only seen power supplies put out a DC current or a DC voltage, both in terms of our class and in terms of the lab exercises. We've always used power supplies that have a constant power output, constant voltage output. In this particular case now in chapter 26, we're going to talk about current that varies in time. Here's a curve that shows how it varies in time. The battery or power supply has a peak EMF, which is E naught, and that varies between E naught and negative E naught at a characteristic frequency F. The frequency we're probably going to see most often in this chapter is 60 Hertz, which is the frequency of power that is delivered to a home. The frequency of voltage that comes out of the outlets in our wall varies at 60 Hertz or 60 cycles per second. So the output of the power supply is sinusoidal. It varies between the positive and negative peaks, E naught and negative E naught of the power supply. The instantaneous EMF is going to be equal to the peak EMF, E naught, times the cosine of 2 pi ft, which varies between 1 and negative 1 at frequency F. And we can always characterize that as well as E naught times the cosine of 2 pi t over capital T, where capital T is the period, and the period and the frequency, you'll recall, are related by an inverse relationship. We call E naught the peak or maximum EMF. Capital T we use as the period of oscillation, and frequency F, the frequency of the oscillation. There's a nice image here in the lower right of some Christmas lights that are being slung around and a photograph taken of them, and at some points they're on and at some points they're off. This is because they are being fed by an alternating current source. They're plugged into the wall, and that wall oscillates at 60 times per second. These are LEDs, which stands for light emitting diode, and it turns out they only conduct current in one direction and not the other. So for half the cycle, for example, when the EMF is positive, the lights light up, and when the EMF is negative, they're dark. And that's why you see this alternating light on and light off pattern. But the point of this diagram, or this picture, this time-lapse photograph, is to show you how if you twirl them around, we can actually see in a photograph how they go on and off, even though we don't see it when we look at them when they're sitting in front of us lit. And that's because the frequency is high enough so that the eye and the brain can't sense the flicker, or it's barely on the verge of that, so we don't generally see it as flickering, which is much more pleasant. Okay, let's talk about a very simple resistor circuit that's being powered by one of these alternating power supplies. Here's the power supply, the alternating power supply, and here's the resistor. Very simple circuit consisting only of the power supply and the resistor. I want to make mention of the fact that we're going to use lowercase variables, little I and little v, to indicate instantaneous values for voltage and current. Okay, so we're going to use little values indicating instantaneous. Capital values will be reserved for peak values. Okay, so right here you see that the instantaneous voltage, V sub R, which is the instantaneous voltage across the resistor, is going to be the peak voltage across the resistor, capital V sub R, times the cosine of 2 pi ft, which is going to modulate that function according to a sinusoidal shape. Ohm's law tells us that instantaneous voltage is related to the instantaneous current. So here's the expression of Ohm's law. The instantaneous voltage varies between a maximum and a positive maximum and a negative maximum value, as does the current. So if the current is oscillating between a positive value and a negative value, what does that look like? How can we envision that current? Well, think about the case of DC circuits. When we talked about DC, we looked at the motion of electrons bouncing down the wire as moving at effectively a constant velocity through that wire. All the electrons move in one direction. They move in the direction that they are influenced by the EMF, the voltage, and therefore the electric field in the wire that's established as a result of a voltage difference causes the electrons to move in one direction, and they move at effectively a constant speed. The way to look at AC current is to envision the electrons as sloshing back and forth in the wire at 60 Hertz, 60 cycles per second. So It would be like the electrons moving back and forth very quickly. That means they don't go very far. Each electron only travels a little bit of distance to the left and a little bit of distance to the right. And it does so because the EMF that's driving it is constantly reversing direction, because this is an AC source. Kirchhoff's loop rule tells us that at any instant in time, the sum of the voltages in the circuit are going to be equal to 0 at any instant in time. Okay? This is the instantaneous EMF, and this is the instantaneous voltage across the resistor. Why is there a negative sign? Because in going around the loop, we might encounter, for example, a positive voltage across the EMF at a particular moment in time, and that's going to correspond to a voltage drop across the resistor. On the other hand, half a cycle later, if the EMF is pointing down, then that means that the voltage drop across the resistor is positive if we go in the clockwise direction. So, excuse me, the sum of the voltages according to Kirchhoff's law is expressed down here. We have the voltage drop across the source and the voltage drop across the resistor, which is instantaneously equal to E and V sub R, and those always have to sum to be 0. Just because the current is moving back and forth and the EMF is alternating between a positive and a negative value, Kirchhoff's law is still, nonetheless, always satisfied. The loop rule is always satisfied, which is ultimately an expression of the conservation of energy. So this slide summarizes what we've seen so far. The instantaneous voltage across a resistor is equal to its peak value, capital V sub R, times the cosine of 2 pi ft, everything oscillating at frequency f. When in the case of a very simple circuit where we have one resistor, then the voltage drop across the resistor, the peak value of that voltage drop across the resistor, is equal to the peak value of the EMF output of the power supply. The instantaneous current in the resistor, which can be found from Ohm's law, is equal to the instantaneous voltage across the resistor divided by its resistor value. That's always true, even though everything is varying in time. Ohm's law is always satisfied moment by moment. So we can replace little v sub r with its identity in terms of the capital or the peak value of the voltage, capital V sub r times the cosine of 2 pi ft. So when we replace the instantaneous voltage with its expression in terms of the peak voltage and the cosine function, we see that the instantaneous current is equal to the peak value of the current times the cosine of 2 pi ft. In other words, the current also oscillates at frequency f between its positive peak value I sub r and its negative value, peak value negative I sub r. I sub r is therefore the peak current in the circuit, but that peak current is only being realized twice a cycle. Why is that? Well, the peak value, the peak positive value is here, and the peak negative value is here. So it's reaching its peak values twice every cycle. We'll see how this has bearing on the power of the circuit in just a moment. Here we're plotting two different quantities. We're plotting voltage and current on the same axis, which we shouldn't do because they have different units. They're different quantities. We would never say, for example, that 3 kilograms equals 5 seconds because they're different quantities. We can't draw an equality between the two. So this axis is not plotting the same quantities. You can imagine two axes overlaying one another, one for the voltage and one for the current. The voltage is being plotted here in green and the current in blue. And what we can get from this diagram is an understanding that both the voltage and the current, the voltage across the resistor and the current moving through it, are in sync with one another. They are in phase with one another. They both reach their peak values in the positive direction at the same time and their peak values in the negative direction at the same time. We will find out later that capacitors and inductors are different in this respect. For them, the current and voltage are 90 degrees out of phase with one another. Positive 90 in one case and negative 90 in the other. We'll learn about that shortly. So here's the expression then for the instantaneous voltage in terms of its peak value, the instantaneous current in terms of its peak value, and we see how they vary in time in sync with one another. Let's think about the power in the circuit. The power, it's a little trickier because the current is varying in direction. There are times when there's no current, and there's times when there's peak current. When there's peak current, there's peak power output. But as the current moves through the origin and instantaneously goes to zero for just a brief moment, there's no power being dissipated in the wire or the circuit. So how can we deal with that in the case of an alternating circuit? we denote the instantaneous power by little p. Little p is equal to little I squared times R. You'll recall for the DC circuit that capital P was capital I squared R. This was the expression we used for power in a DC circuit. So if that's the case for a DC circuit, it's also the case for an AC circuit, but instantaneously. Instantaneously, P is I squared R, little I squared R, where little I is the instantaneous current in the resistor. We can replace the instantaneous current with its expression in terms of the peak current times the cosine of 2 pi ft to find out that the instantaneous power in a circuit is equal to capital I R squared times cosine 2 pi ft squared. Why squared? Because both I sub R is squared and the cosine is squared because originally the power is proportional to the current squared. So, what does that mean? It means that the power oscillates at twice the frequency of the EMF supply. Why? If power is proportional to I squared, the square of a positive number is positive, the square of a negative number is positive. So if you actually square a sine curve, you end up getting something that looks a little bit like this. The square of the positive peaks are positive, the square of the negative peaks are positive. So since the power is proportional to the current squared, then the bottom diagram shows what happens with the power. It oscillates twice per cycle. Here's one cycle of the EMF, and during that cycle, the power oscillates between two of its cycles, or it oscillates through two of its full cycles. The power is maximum when the current is, let's say, in the right direction at its peak value, and the power is also maximum when the current is going to the left, or negative at its peak value. Therefore, the current in a light bulb reverses 120 times per second. Here's one time when the current reverses, here's another. In the course of one full cycle, the current goes through the origin twice. And that means that the power drops to zero twice. The maximum power is reached twice per cycle. This raises the question, how do we characterize the average power output? We know that the power varies in time, but it wouldn't make much sense to characterize it as a number unless we can talk about an average. So the average is more useful. We denote the average power by capital P sub R, which is 1/2 I squared R. And the reason for that is because the area under this curve, you can think of the area under the power curve like this over time constituting the total power output of this circuit. The area under this curve is equal to, the sum of all those areas is equal in time to the power output of the circuit. So that area, it turns out, is equal to the area of a rectangle with exactly half the height of the peak values here. How does that work? Well, very, very quickly, you can sort of see how this area right here can be plunked down into that little cavity there, and this peak right here can be plunked down in that cavity to make what ultimately will give us a rectangle of area. So that's where the 1/2 comes from. It turns out the height of the line under which the area is equal to the sum of all of the area under the oscillating curve, it happens at half the peak value. So at 1/2 I squared R, right here, that ends up being the average power output. Okay? So in an AC circuit, the power is 1/2 I squared R. In a DC circuit, the power is I squared R. We have to keep that distinction in mind. So since we have these two different expressions, we have an expression for DC power and AC power, which differ by a factor of 1/2. Let's see what we can do about that. Just to remind you, here's the expression for DC power. DC power is P sub R equals I squared R. The power in a resistor dissipated by that resistor is equal to the current squared times its resistance value. We can also express that in terms of the voltage V. But in the DC case, the voltage V and the current I are constant numbers. They persist in time at the same value. In an AC circuit, both the current and the voltage vary in time. And we find that for an AC circuit, we have a factor of 1/2 in the power expression. let me just remind you, we just, on the previous page, we learned that the power in a AC circuit is equal to 1/2 times I squared R, where I is the peak current. And we need that a factor of a half because the current is varying, and over time the average value of the power is 1/2 I squared R. So in that case, we can define two new quantities, an RMS current and an RMS voltage. The RMS current is defined as the peak current divided by √2, and the RMS voltage is the peak voltage divided by the square root of 2. That way, when they are squared, for example, when the current is squared in the power expression, we get a factor of a half, which is what we need in the for the AC circuit. So we can express the power, the average power in an AC circuit, as the RMS voltage squared times the resistance, or the RMS voltage squared divided by the resistance. And this ends up being I RMS V RMS. This is the expression then for the power dissipated in a resistor in an AC circuit. As long as we use the RMS current and the RMS voltage, then the power is equal to I RMS V RMS. In the case of DC, it's also equal to I times V, where I and V are constant values. So there we see the similarity now. For an AC circuit, we can take the current times the voltage to get the power. For a DC circuit, we can take the current times the voltage to get the power. The only difference is in the AC case, we need to make sure and take the RMS values, which is the peak value divided by the square root of 2.